Hey there, young physicists. Have you ever watched the audience doing a wave in a stadium? The people don't actually move across the stands, but the wave of excitement travels all around. That's exactly how a progressive wave works in physics. A progressive wave is simply a disturbance moving through a medium, passing energy from one point to another without anyone actually shifting places. The particles just vibrate where they are, each taking turns to move up and down or back and forth. Each one moves just like its neighbor, only slightly out of step. That's what we call a constant phase difference. So, imagine a chain of people doing the same dance move, perfectly timed, one after the other. That's a progressive wave in motion. Let's get mathematical, but don't worry, no pain, no panic. We describe a progressive wave with the equation y of x and t equals a sin kx minus omega t plus phi. Here, a is the amplitude, how big the dance moves are. K is to pi divided by wavelength, showing how many waves fit in 1 meter. Omega is to pi times frequency, how fast the wave oscillates in 1 second. And phi tells us the starting point of the vibration, like your dance position before the beat drops. If the wave moves in the positive x direction, we use the minus sign before omega t. If it travels in the opposite direction, we flip it to plus. So, that minus or plus isn't just decoration, it's like an arrow telling us which way the wave is going. Okay, now that equation looks packed, but every symbol is telling a story. Amplitude, A, is the energy carrier. The bigger the A, the louder the sound or the taller the ripple. Wave number, K, is how tightly the waves are packed. More waves in a given distance means higher K. Angular frequency, omega, is how fast things shake. More shakes per second, higher omega. Phase constant, omega, decides where each particle begins its motion. It's like everyone's personal timer offset. And the magic term, kx minus omega t plus phi, is the phase, the dancer's exact step in the choreography at that moment. So, let's talk about what happens between two particles in the wave, say, one at position x and the other at x. The phase at any point is theta equals kx minus omega t plus phi. So, the phase difference between the 2 points is delta theta equals k times delta x, or in simple words, 2 pi divided by lambda times the distance between them. That means, if 2 points are one wavelength apart, their phase difference is a complete 2 pi radians, one full cycle. In a wave, as we move along the direction of propagation, this phase difference builds up smoothly. It's how the wave keeps its shape while moving forward. Now here's the fun part. Not only do particles move, they move fast and change speed. Let's start with the displacement equation, y equals a sine kx minus omega t plus phi. If we differentiate with respect to time, we get v sub y equals negative a times omega times cos kx minus omega t plus phi. That's the particle velocity, how quickly a point moves up or down. Differentiate once more and we get the particle acceleration, a sub y equals negative a times omega squared times sin kx minus omega t plus phi. The maximum velocity is a times omega and the maximum acceleration is a times omega squared. But here's the twist, velocity leads displacement by 90 degrees and acceleration leads by 180 degrees. It's like a pendulum, fastest at the center, slowest at the edges. Alright, time for a neat derivation that every physics student should memorize like a magic trick. We start again with y equals a sin kx minus omega t. For a fixed point on the wavefront, the phase kx minus omega t stays constant. Now, if we differentiate that phase condition, we get k times dx by dt minus omega equals 0. which means dx by dt equals omega divided by k. That's a wave velocity. V equals omega divided by k. Since k equals to pi divided by lambda and omega equals to pi times f, we can rewrite it as V equals lambda times f. This shows the speed of a wave depends only on the medium, not on amplitude or phase. Time to wrap it all up like a perfect standing ovation. A progressive wave is a moving disturbance that transfers energy through a medium, not matter. Its displacement is given by y equals a sin kx minus omega t plus phi. Every parameter, a, k, omega, phi, tells part of the wave's story: amplitude, wavelength, frequency, and phase. Direction of propagation. Check the sign before omega t. Wave speed. Always V equals lambda times f. From sound in air to ripples in water, every wave we experience follows these exact rules, the universal rhythm of motion. Sign off, and that's how we understand the displacement relation in a progressive wave, the physics behind every ripple, every sound, and even every vibration you feel.